In this video, I want to have a look at a typical advanced electric field problem. Here is the problem. We have 2 point charges, one at the origin with a charge of +3 microcoulomb, and then we have one at 3 centimeters in x, 1 centimeter in y, which has a value of -2 microcoulomb. The question is, at what point, besides infinity, is the electric field 0? I know that the electric field of a positive charge will point away from it, while the electric field of a negative charge will point towards it. So we can kind of think where are possible candidates for where the sum of these two fields is 0. If I go to some random location like here, the one from Q1 will point away, while the one from Q2 will attract. So it's impossible that these two vectors add up to 0. So random locations are not possible. What about in between somewhere along this line here? Let's make a line here that connects the two. If I go somewhere in between, the one from Q2 will attract, the one from Q1 will repel. So also here it's not possible to add up to 0. In between would be a candidate, however, if my charges would have the same sign, because then only somewhere in between could their fields add up to 0. What about down here? Well, yes, now Q3 would repel, but Q2 would attract to it, so that's possible, as well as somewhere up here where the one from Q2 would attract and the one from Q3 would repel. Now, is it somewhere down here or somewhere up here? For that, we should look at the values. Remember, the electric field becomes weaker the further you get away from it. So in order for the two vectors to be able to be of the same length, we have to be closer to the charge with the lesser magnitude in charge. So in this case, closer to the -2 microcoulomb, so somewhere up here. So what we're looking for is actually the vector that goes to this location here, R. So we want to know that vector R that goes to that location where hopefully those two fields add up to 0. In order for the two fields to add up to 0, their magnitude must be equal. So I can write that the magnitude of field 1 has to be equal to the magnitude of field 2. And then I can just plug in information. So I have my distance from Q1. I'm going to call the distance from Q1 R. So I have KQ1 over R squared, absolute bar of this, is equal to, now what's my distance from this one? Right, that's R minus the distance between the objects. So I have K times Q2 times R minus the distance between the objects squared. Most of the work is already done. From now on, it's just a question of math. So a lot of things cancel out. And then let me write the charges in it. So I have 3 microcoulomb over R squared is, because we use absolute bars, plus 2 microcoulombs over R minus A squared. The microcoulombs cancel each other out. I can cross multiply. 2R squared is 3R squared minus not R squared. 3R is 3R minus A squared. A couple of math manipulations later, I get my standard form for the quadratic equations and I can solve for R. When I plug this in my calculator, I will get two answers. One is 1.74 centimeters, the other being 17.2 centimeters. Looking at the problem, I can easily see that this one is the solution. So the other one would actually have been the solution if both charges would have the same sign. So now how do we get to that, to a vector? Fairly simple. We take that magnitude, so 17.2 centimeters, and we go along a vector that points in that direction. So that vector in our case would have been 3 to the right and 1 up. And we divide this vector by its own length. And this will give us the position from the origin where the total electric field will be 0. When I punch the numbers in my calculator, this is what I get. 16.3 along the x-axis and 5.5 centimeters up is the location where the net electric field is 0.